that time average potential here looks like this. And these little lines here are the motional states of the ion. To calculate what it is, you have to take the gradient of the voltage and square that, and that gives you how the characteristic potential right here. The equation for motion of this has two components that I'm going to point out. One is the secular motion, and that corresponds to this harmonic trap right here. And that's at a frequency omega, which is much less than the drive frequency, big omega. So typically in our traps, we use drive frequencies of 30 to 50 megahertz and generate secular frequencies of about 1 to 3 megahertz. Another component of that is this micromotion component. And that term is always going to be there, and it's this small oscillation of the ion at the drive frequency. Actually, when you incorporate this term, it's at the drive frequency plus or minus the secular frequency. So you have this other component here, and that is something that we want to minimize. Now, it's minimized sort of naturally by the fact that there's a factor in front of it that's based on the ratio of little omega to big omega. But one of the critical parts to minimizing that is you have to balance all of your electric fields that are at the RF node of the ion. So if you have an RF node where the ion wants to be, and you have a biased electric field that's trying to push the ion away from there, then your micromotion term is typically higher. So we do a lot of compensation looking at the line width and things like the line width of the detection transition in order to minimize this micromotion term. There are multiple trap geometries that can be actually used to trap an ion. They just have to give rise to this electric field gradient to that gradient of the voltage squared. And so I'm showing a few right here just as representative of ones we have used in both the microfabricated traps as well as the manually fabricated traps. The first one I'll talk about is this two-layer trap, and I've depicted that as a series of 4 wires. There are 2 DC wires, or 2 static electrode wires right here where they're segmented with U1 DC voltage, U0 DC voltage, and so on. And then the other 2 wires have RF applied to them. And this is a transverse cross-section of the trapping potential, so the secular trapping potential. And that shows that you would get a trap in this region. Now, in order to compare these different trap geometries, I've normalized this so that this has a secular frequency of 1 and depth of 1. And then I've looked at other different trapping geometries, or actually this is outlined in this paper by John Chiaverini, with other trapping geometries in which you keep the voltage and frequency applied to the trap the same, as well as the distance from the ion to the nearest electrode. So in this next geometry, which is a single layer trap consisting of 2 RF wires here in the middle and then 2 outside DC wires, you would get a somewhat smaller trap secular frequency, but your depth would really go down. And so these are things that one has to consider with building, say, microfabricated traps in which the voltages are limited and you need to maintain a high enough depth to be an operable trap. And then the other geometry I'll show is the 3-layer trap. So that has 2 RF electrodes here in the middle, and then the 6 or the 4 outside electrodes are all DC voltages that are segmented. And that gives a secular frequency of half of what the 2-layer trap is, and then a depth of 0.078 of what the 2-layer trap is. Okay, moving on to the idea of motional heating. This is a concern for us because, so I showed you the picture of the ion in the harmonic potential, and if there were no fluctuating electric fields where the ion is, it would stay in its same motional state. However, the problem is that these electrodes have electric field noise sources on them, and that tends to heat the ion and increase their motional state, and that's something we want to limit. So we investigated the source of this motional heating in a series of experiments. This is a plot of historic data from not just our traps, but from other traps and other groups using a variety of different ions. And you can see kind of a trend here. The bottom, the horizontal axis is the trap distance from the electrode to the ion, and this vertical axis is the spectral density of electric field noise. And you can see this sort of correlation here, where as you get to really small traps, the spectral density of electric field noise that the ion sees increases. And it turns out that that scales, this line here is sort of meant to be a rough guide for the eye, but that scales at about 1 over d to the 4th. So now you can see kind of why this is a big concern for us for small traps, because as we get to these small regions, we're going to have really high heating rates. The other thing you can see from this is we can tell that the source of noise is not just Johnson noise on the electrode, because that level of noise is way below what we actually measure. In addition, Johnson noise follows the scaling law of 1 over d squared. So in these experiments, we tried to characterize that electric field noise. And what we did was we set up an experiment where we had 2 needles. And this is not a trap I showed you before, but what it consists of is a needle like this and a needle like that, both of which have RF voltages applied to them. To estimate or to measure the amount of electric field noise that a little patch of voltage noise on the needle will cause, and by the way, that's what this noise is called, patch potential noise, because we describe it as a little patch of voltage that fluctuates. So the way we describe the effect it has is we parameterize it by saying, all right, if I have a voltage noise here of that patch, what is the electric field that it caused at the ion? And that number, so that relationship is parameterized by that psi value, and that psi depends on, well, where is the patch relative to where is the patch on the needle, so that's the n, what is the size of the patch, s, and also what is the distance from the ion to the needle tip. And so this is sort of a number that's going to be different for all different geometries. And to make a good estimate of this, we have to do computer simulations in order to calculate what that relationship will be, just because the geometry is more complicated than we can solve analytically, at least easily.
I'm sorry, I'm getting that. Now, those things like STM, right? So you remember when you have a nanometer from the state.
Sure.
So
this is a similar noise that is observed in those systems.
Do you have anything from there? If you go to your previous graph.
Oh.
So then we are not in microns, but we are a nanometer from the thing.
Right.
So what do I get if it is scaled with 1 over d4?
Well,
does it happen in the STM?
This patch potential noise does happen in the STM. But from our calculations, if you're looking at what the distance scaling is, if you were within a nanometer from your surface and the patches are of the order of microns, then that would look like a correlated noise source compared to what the tip is. So most likely in that really short distance range, it would follow 1 over d squared relationship. But it would still be, I mean,
so
it's
there's a
depending on
crossover depending on the
Yes.
patch size. So this scaling would change.
Right. And that's also a source of noise that's observed in other systems. The one that comes to mind is someone, Adelberger, I think, gave a talk about measuring gravitational differences at really small length scales, and he observes also this sort of patch potential noise.
It's just the other one is the Casimir effect. In the Casimir,
Right.
You should mention that all this data is at 1 megahertz.
this is all in one.
All the points are at 2 megahertz. Whereas the gravity experiment and even SPM stuff is done at very low frequency. Very, very low frequency.
How does the patch noise change with frequency?
I have a